that data is stored there, but it has at least two pointers, one to the left and one to the right. So, you know, if this is the node U, this would be U dot left and U dot right. And if one of these subtrees is empty, then this would just be set to null. Okay. So easy to implement. So we have this terminology of, let's just pretend this is a picture of a node inside a much bigger tree. So we said over here is, so let's call this U. This is U's left child. This is U's right child. If we're going to stick with this kind of terminology, then we'll say that this thing up here must be U's what? Parent. It's kind of a strange terminology because I'm not sure how it ever developed this way, but it's kind of weird because everybody in this binary tree world has only one parent, and they all have exactly, well, at most two children, which is not the usual thing. But whatever, it's just the way this terminology developed. You can't change it now or else nobody will understand what you're talking about. We also extend that. So for example, we have a node down here. In fact, we have nodes in this whole subtree. And in this subtree, all of those things are U's descendants. Right? They're U's children and the children of U's children and so on. Down here, we have a node, and so let's call this node W, and we would say U is W's what? Grandparent. Right? It's the parent of, U is the parent of W's parent, so grandparent. And this guy up here, I don't know, let's call him X. We say things like X is an ancestor of, well, pretty much everything in this picture. He's an ancestor of U, he's an ancestor of W, he's an ancestor of everything in all of these subtrees here. So we adopt this kind of family tree terminology, even though it's a bit sketchy that this isn't really what families necessarily look like. Okay. So a few more things. The depth of a node U is equal to the distance from U to the root. So for example, the root itself has depth 0. This node has depth 1. It's one step away from the root. This node has depth 1. It's one step away from the root. And all these nodes here have depth 2. They're 2 steps away from the root. And these ones have depth, this one has depth 3. It's 3 steps away from the root. So we have depth. We might talk about level I is the set of nodes with depth I. So level 1 is these two nodes, level 2 is these two nodes, level 3 is this node, level 0 is just the root. And we also talk about the height of a tree is the maximum depth of any node in the tree. Okay. So what's the height of this tree? 3. There's a node of depth 3, and there's no nodes of depth 4 or greater. So the height of this tree is 3. Height is a good term for it. And if you think of each step here as being 1 unit, that tells you how many units there are in total. Okay. And, you know, why do we call these things trees? Well, that's because it's not always obvious from this standard way of drawing them. But if we turn this picture upside down, then yeah, we do have something that looks kind of like a tree, right? There's something that's a bit more tree-like. That's still a binary tree that looks more like a tree if I draw it in a more careful way. So that's why we call them trees. Okay. Any questions so far? So far it's all just definitions. So, yep.
Just to continue the terminology, would the other child or node that has the same parent as another one be called a sibling?
Yep. These two nodes here are siblings. And you don't see it so often, but what would you say about these two nodes? You might call them cousins. You don't see that used too much, the term cousins, but siblings definitely. You often say sibling because otherwise it's kind of awkward to say something like the other child of the current node or the other child of the parent of the current node. So it's easier to say sibling. It actually, programmatically, it is a little bit annoying sometimes to find your sibling because the only way to find your sibling is to go through your parent, and then, well, your parent has 2 of them and you want the one that's not you, so it's actually a little bit annoying to write the code for that, but it's doable. Yeah.
Is the last node literally just called the end node?
Is it just called what?
The end node?
What's the last node? What's that?
What's the name of the last node?
So what's in this picture? What are you calling the last node?
Yeah.
What is it though? Which one?
It's 2.
This one?
Yeah.
And why not this one?
Well, the end node.
Yeah. Okay. So good question. What are those things? Do these things have special names? Anybody want to guess? These guys here. These are leaves. So for some reason, we leave the terminology of families behind, and we suddenly go back to the terminology of, trees like in a forest. That's these guys here. Yeah, that's sort of where the leaves are. They're at the end of the branches. Yeah. In between the root and leaves, is there a trunk and branches? There's no natural trunk, unlike a tree in a forest, except possibly the root itself. Branches, yeah, you might call these branching nodes. More likely, you call these things that are not leaves, so that's these guys. You call them internal nodes. So there's 2 kinds of nodes, the internal nodes and the leaf nodes. the leaves have no descendants. Yeah, they could have used a different name than leaves. I don't know, whatever you call somebody who has no children. The bachelors or bachelorettes, I guess. Okay. All right, so what are these things good for? I said that computer scientists love them and that they have all kinds of applications. So let's look at 3 such applications. So application 1. Let me give myself enough space here. Application 1, expression trees. So if you study compilers, these come up a lot. Even if you study simple compilers, things like even calculators, these things come up. So if I have some expression like a plus b times c plus d minus e. There's an expression, and you can write this in most programming languages, and this will get compiled to something that evaluates this, which must mean that there's some internal representation of this. And one of the most common internal representations is something called an expression tree. In an expression tree, the internal nodes are these operators here: multiplication, subtraction, addition, division, whatever. So the internal nodes are these operators. And the 2 children of a node, so one thing about all these operators is that they're all binary operators. They have an argument on the left and they have an argument on the right. So they have 2 operands. And so the children of a node are its 2 operands. So here I have a multiplication operation which has 2 children, or 2 operands. On the left is a plus b, and on the right is c plus d minus e. So on the left we would have the tree that represents a plus b. And on the right, we have the tree that represents c plus d minus e. Addition and subtraction are at the same level of precedence, so we do them left to right. So the left-hand operator of this plus is the c. The right-hand operator is the expression d minus e. So any expression that is made up of binary operators this way, we can write it equivalently as an expression tree like this. A binary tree whose internal nodes are the operators and whose leaves are they're either literals, meaning constant values, or variable names. In this case, they're all variable names. All right. Now let's think about in an expression tree here. So if you give me an expression tree, I need to, at some point, want to evaluate this expression. So how would you do that? So I want to know what value comes out of the root here. And, maybe A, B, C, D, and E, they all have some numbers assigned to them that we can look up in some table somewhere. How would you figure out?
So we'll start finding the leftmost root.
Too complicated. And we should be careful here. Well, we'll see how we do it. But there is an order of operations implied by this tree, the fact that I didn't draw some other tree with the same labels. Yep. Still too complicated. Yep.
Perform the operation if it knows only 2 subjects.
perform the operation on the node, on the what? To evaluate a node, we need to perform the operation at that node on the result of evaluating the two subtrees. So it's a recursive algorithm. So there's basically two cases. Let's say you want to evaluate the subtree rooted at R, then two things happen. If R is a leaf, well, then it's just one of these things, and there's a specific value associated with that thing. So we would say something like return, value of the variable or constant in R. Otherwise, if R is not a leaf, then we do something like, say, x is equal to evaluate R dot left, y is equal to evaluate R dot right, and then we return x and whatever this thing's operator is with y. So if this thing is a plus, then we return x plus y. If this thing is a multiplication, we return x times y, or whatever. So there's a really simple recursive algorithm for this. Either it's a leaf, in which case it's just a value, we return it, or it's one of these internal nodes. It has two children. We need to know the values of the two children before we can figure out what the value of this node is. So nice and easy. All right. So that's one application. Another one, which was hugely popular for the last decade or so, and still is important, but is further outside of computer science, are these so-called phylogenetic trees. So these are things that are supposed to represent evolution of a series of species over time. So for example, here are some species: humans, apes, birds, fish, and these are not even species, these are big groups of things. Spiders, ants. So the leaves in the tree are some kind of species, usually what are called extant species, meaning still alive. They still exist. And the internal nodes represent what are called speciation events. So what's a speciation event? Well, that's something like this, where you had some species that, or some population of things that could all mate with each other and reproduce, and so that defines, in some sense, a species. And something happened to those two things. Maybe they got separated, or something happened to this population. Maybe it got physically separated. The island that they were all living on actually broke because of some event. Actually broke into two pieces, so there was an ocean between them now. And after a while, those two things start to evolve separately, and they change so much that they're no longer able to mate with each other anymore. And that means that they've now become two different species. So these internal nodes here are called speciation events. And that's where this one population of things suddenly becomes two different populations that diverge genetically enough that they're no longer considered the same thing. And, you know, we get a whole history of these things. And somewhere up at the top is some root, which is like some piece of slime that grew in some weird, salty, hot ocean environment that's like the original source of life on the planet. So these binary trees are a good model of these things. Usually in here, they're drawn quite differently. In computer science, we like to draw them sort of level by level like this. In biology, you would probably treat this axis as time, you know, some number of billions of years ago or millions of years ago up at the root, and now down here. And you really try and place these nodes at the point in time where you believe that this separation happened between these two species. So that's an application outside of computer science. And the one that we're going to be most interested in, focusing on the most in this course, is a binary search trees. Okay. What's a binary search tree? Well, it's a binary tree. Let me draw one of those. Let's keep it small. So it's a binary search tree, or it's a binary tree. At each node, there's a value. So let's put a value here. Maybe we tend to use numbers, but it can be anything that you can sort. So anything from a total order. And we maintain this property that so at the root, there's some value. The left child is also a binary search tree. And everything, so let's call this a binary search tree containing only values smaller than 10. And over here on the right side is a binary search tree containing only what? Values, let's say greater than 10. Keep our lives simple, we'll assume that no value appears twice in the binary search tree, so there's no equals on either side here. You're either less than or bigger than. Okay. And of course, this applies inductively, so here we might have a 5, which means in the left child of this thing, we need something smaller than 5. Let's put a 1. In the right child, in all of this subtree, we need things that are bigger. So let's put 7, 6, 9. Over here, we need things bigger than 10. So here is 15. And what value should I put here? Something smaller than 15, but bigger than 10. So 12 is a good one to put there. Okay. That's a binary search tree. Okay. So it has a root that contains a value. It has a left value, let's call it x. It has a left subtree, which only contains, is a binary search tree on values that are less than x, and it has a right subtree, which is a binary search tree on values that are bigger than x. That's the whole thing. Okay? Now, these things are incredibly useful. Well, what are they useful for? In most libraries, whatever you call a sorted set in your favorite programming language, whether it's Java's sorted set, C++'s set, and Python doesn't really have a great standard one. It has a sorted set too. It's usually implemented as some kind of binary search tree. And the reason is that it tends to be, if you use the right kind of binary search tree, it tends to be fast to look for things in here. So for example, if I, in this tree, want to find the value 6, well, I have to start somewhere, and the natural place is to start at the root. So if I start at the root and I'm looking for 6, what should I do? And why should I do it? Yeah? Yeah. So I can compare 6 and 10 and see that 6 is smaller than 10, and everything smaller than 10 is in the left subtree by the definition of binary search trees. So I should go looking in the left subtree. Now I'm looking in the root of the left subtree. There's a 5 there. 6 is bigger than 5. So if it's in this tree, it has to be in the right subtree. So I go looking there, which takes me down to 7. 7 is bigger than 6. So if 6 is in there, it's in the left subtree. And indeed, at this point, I compare this value and 6 and realize this is the value that I'm looking for. Okay? Good. Let's look at another example of that. Let's look for 13. I start at the root. Where do I go next? The right. 13 is bigger than 10, so if it's in there, it's in the right subtree. Now I see 15. So if 13 is there, it's in the left subtree. Now I see 12. So if 12 is in, or sorry, if 13 is in there, it's in the right subtree. Well, now I fell out of the tree. I didn't find 13. So what did I learn from this? Well, I learned the obvious thing, that 13 is not stored in this tree. Is there anything else that I learned? Yeah. Here that contains 13, and the whole thing would still be a binary search tree. Anything else that I learned? Yeah. I've learned some stuff from this path here. Yeah. Yeah. So, at some point in this last step, I fall out of the tree, meaning that at each step, I've guaranteed that if the thing I was looking for is in the tree, then it's in this part of the tree, and at some point, there's nothing left in the tree, so I know the thing that I'm looking for is not there. Let's take a look at these two guys here. So here's a place on this path. Let's see what I did. So here, I went to the right child. Here I went to the left child. And here I went to the right child, even though it wasn't there. So if I look at the last place here that I turned left, I see 15. Anything special about 15 in this set as in terms of as it relates to 13? Yep. Yeah. So if I follow this path, then the last place I turn left is the smallest value in the set that is greater than the one that I'm looking for, 13 in this case. So then what about the last place I turn right? Yep. Yeah. So the last place I turn right is the largest value that's smaller than the thing I'm looking for. Right? I mean, let's write these down. 1, 5, 6, 7, 9, 10, 12, and 15. Well, where does 13 fit into that sequence? Right there. Right after 12, the last place I turned right, and right before 15, the last place I turned left. So actually this path doesn't just tell me that the thing is not there. It tells me, well, it's not there, but here are the two closest things, the closest one on the left and the closest one on the right. Is that always the case? Yeah. So what about 9? Well, let's look at the path for 9. So we'd start at 10. We go left, and then we go from 5. We go right. From 7, we go right, and then we stop because we reached it. So this path turns left here, turns right here, turns right here. So the last place it turned left was up here at 10, which is what comes right after 9. And the last place it turns right was at 7. And if you look at 9, there's the 7, and there's the 10. Yep. Yeah, so, well, let's not look at 1, let's look at 0. So if I search for 0, it's smaller than 10, it's smaller than 5, and it's smaller than 1. So what is that telling me? So I did make some left turns. The last place I turned left was at 1, which means 1 is the smallest thing that's bigger than 0. But I never made any right turns. What is that telling me? It's telling me that there's nothing smaller than 0 in the set. Okay? And indeed, this is where 0 fits into this sequence. Right here, before 1, there's nothing on the other side. So if I never make a left turn, if I never make a right turn, that means I'm just walking down this left wall of this tree because there's nothing in the tree that's smaller than what I'm searching for. And if I never make a right turn, if I never make a left turn, if I only make right turns, I walk down this right wall of this tree, it means that the thing I'm searching for is bigger than everything in the tree. So if I search for 16, I'll fall out here. Only right turns. The last one was at 15, and indeed 15 is the thing it's the largest value that's smaller than 16. It's the largest value in the tree. So that applies a few things. If you want to know what's the smallest value in the tree, you just keep going left from the root. If you want to know what's the largest value in the tree, you just keep going right from the root. Okay. So notice that's very different, for example, from what we get when we look up something in a hash table. In a hash table, we take our element, we hash it. That takes us to some list, which is probably a really short list. And either the thing we're looking for is in that list or it's not. If it's not in that list, that's the only thing we learned. We just learned it's not in the list. It says it's not in the table I have no idea what's bigger, what the next closest thing is in the table or not. That doesn't help at all. So hashing does not do that at all. Binary search trees, on the other hand, do that. They tell you, well, if it's not there, they'll give you where it should be and what are the two things in this sorted order that would be on either side of it. Okay. All right. Any questions? Good. So this is important. We're going to be doing at least 3 different kinds of binary search trees in the next 3 classes. So understand what's happening here. Let's leave expression trees. Phylogenetic trees are not so important. So we've seen over here, we kind of wrote down an algorithm for evaluating a node, the value of a node in an expression tree. Let's try and do some other things, see if we can solve some other problems on trees this way. So for example, one of the terms I forgot to mention, the size of a tree is the number of nodes in the tree. Okay. So, if I want to know the size of a tree rooted at the node R. So the number of nodes in the tree rooted at R. How would I compute that? Yep. Yep. Well, so it's a recursive algorithm. So you say return the size of R's left subtree plus the size of R's right subtree plus 1. Right? The size of this thing is number of nodes in this tree plus the number of nodes in this tree plus this extra node R that we're looking at now. Is that the whole thing? It's a recursive algorithm. What do recursive algorithms or functions need? Base case. So what's the easy base case? When do we not recurse? Yeah. I would argue that there's an even simpler base case. Yeah. If R is null, then it represents an empty tree. How many nodes are there in an empty tree? There's 0 nodes in an empty tree. So there's recursive code for computing the size. If you make a leaf a base case, then you still have an issue that this code will break at a node which has only one child, because you'll recurse on this child, and then you'll recurse on this thing which is null, which means you have to check for null anyway. So since you're already doing that, you might as well make that the base case. Okay, so that's how we get the size. How about the height? So height is the depth of the deepest node. There's a picture. The height is the depth of the deepest node. So that's supposed to return somehow this measure here of this tree. How would you do that? Yep.
You could return the max of the left and the right.
Yep. So you return the maximum of the height of r dot left and r dot right. Sorry. Height of r dot right. Is this correct? Return the max of the heights of the two subtrees? Yeah. Before the base case even. Is this correct? Yeah. Plus one, right? The height of this tree here is one less than the height of this tree because there's this one extra level on top. So we need a plus one here. And we need a base case. What's the base case? The base cases can be telling here. Yep. So you say the same base case, meaning if r equals null, then we return what? Return 0. Let's check that. So let me draw a couple of trees here. So in this box is a picture of a tree. In this box is a picture of a tree. And let's say in this box is a picture of a tree. What's the height of this tree? Right? This says depth 0, depth 1, so the height is 1. What's the height of this tree? 0. So what's the height of this tree? There's only one answer that makes sense. All right. So now let's say we'll be at some node u, which will start at the root. So the picture looks like this. We have the root. This is equal to u. There's a left subtree and a right subtree. And this special thing is supposed to, in some sense, represent the parent of the root. Okay. So now we will say, while some condition is true, don't know what it is yet, we'll have to figure that out. We're going to figure out what to do next. Okay? So there's three cases. Either we're arriving from the parent of u, so prev is the parent of u, in which case we go left. So we say if the previous node is equal to u's parent, and then we have this annoying condition, or the previous node is equal to special, and u is equal to the root. Then we want to do something like u equals u dot left. But before we do that, we should say prev is equal to u is equal to u dot left. Okay? What's the next case? if the previous is equal to u dot right, u dot left, that means we got to u by coming from this left child. We should go to the right child. Prev is equal to u equals u dot right. Otherwise, we didn't get there to u from the parent. We didn't get to it from the left child. We must have got to it from the right child. Prev is equal to u is equal to u dot parent. Okay. And then what's the termination condition? Well, the termination condition could be something like while, so we would want to stop when we come back from here. So while u is not equal to r, or prev is not equal to u dot right. If both of these happens, u is equal to r and prev is equal to u dot right, then we should stop at that point because the next step would be out of this thing. Okay. So that's roughly the code for doing one of these traversals. I say roughly because there's a little issue here that there's points where we're setting u equal to null, and actually the code has to have some annoying stuff here that includes a check when you walk off into a null node that you just don't do that. You just come right back to u in that case. You can look in the book for how that works. No, I meant or. This is a continuation. This is the condition that should be satisfied if I continue. No, I'll enter the loop because prev at the first time is special, not u dot right. Yeah. Sorry, there was another question? Yeah.
This isn't exactly related to the traversal, but with the parent thing, you said initially that the binary trees have a left child and a right child and then like their data or something?
Yeah.
And they also have the parent connection as well?
Yeah.
Okay.
I mean, if you want to be able to do this kind of traversal, you include parent pointers. Okay. So now, adding in the few extra little bits that you need to really make this code work, you see that actually we can use this code to do these things, like compute the size. We know that we visit each node in this traversal 3 times. In fact, we will visit each node once for the last time as we come up from its right child. So if we wanted to compute the size of the tree, we would just say something like size equals 0, and as we come up from the right child, size plus plus. At the end of this process, the size, once this is done, the size is equal to the number of nodes in the tree, because it's equal to the number of times we walked across a node like this, which we do to every node in the tree. If you want to compute the height, well, you keep a variable to keep track of the depth. When we go down from a node to from its parent, well, when we go down to the left child of a node, we increase the depth. When we go down to the right child of a node, we increase the depth. And when we come up from the parent, we decrease the depth. And just outside of this, you would say something like, so start with height equals 0, and say height is equal to the max of d and height. So now this variable d is tracking the depth of the current node. Each time we change it, actually I think this has to go at the end, but that's fine. Each time we change it, we see if that's bigger than any depth we've ever seen before. If so, we update the height. At the end of this process, you know the height of the tree. So all these things you can do with recursive algorithms. You can do with this non-recursive traversal. And this has the advantage of being able to work for trees that have height 1,000,000 with no problem, whereas the recursion one will always blow up on trees that are that high. All right. Here's another problem to solve. Suppose I give you a binary search tree, and I want you to print out its values in sorted order, like this. So for this binary search tree, I would like you to print out 1, 5, 7, 9, 10, 12, 15. What would the code look like for that? Let's start with the recursive code. So I have a binary search tree rooted at R. I want to print out its values in sorted order. What should I print first? Yeah.
The first thing you should do is traverse to the left.
Yeah. So I should print out the values in the left subtree. Because they're smaller than all the values in the right subtree. What should I print out next? I should print out the value at the root. Let's call that r.x. And then what do I do? Yep.
The right tree.
And I should print out all the values that are bigger than the root. And so what's missing from here? It's a recursive function. It needs a base case, which is, what's the easy one? What's the easiest tree to print out all the values in? The empty tree. So if r equals null, just return. Don't print anything. Okay. So that does, that prints out the values in sorted order. We print out all the values smaller than the root, then we print out the root, then we print out the values bigger than the root. So here we print out all the values smaller than the root, that's these guys, then we print the root, then we print out the values bigger than the root. Okay? How do I add that to this code? So in this picture, when do I want to print out the value x stored here? Is it when I'm walking this way? It's when I'm returning from the left and going to the right. So that would be right here. If I want to print out the values in a binary search tree in sorted order, I stick it in this code as I'm going from the left to the right. You can kind of read these things off because there's somehow a difference here between this code for printing and this code for, let's say, computing the size. And that's really because when we print, the work that we're doing at the current node happens in between the left and right recursive calls. When we're computing the size, actually the work that we're doing happens after we did the left and right recursive calls. We add one and we return. So that's why, for instance, when we're computing the size, we put that in this third branch. When we're computing the, when we're trying to print in order, we do it in the second branch as we're crossing here. So this was print. This was size plus plus. And there's some applications, but not that many, where you would actually want to do it on this branch here. So this is called in order if you do it as you come from the left to the right. If you do your work here as you're leaving the subtree, that's called post order. And if you do it over here, that's called pre-order. I don't have a good example of a pre-order thing right now. But sometimes, I mean, sometimes you do work in two of these three or in all three, depending on the problem that you're trying to solve. Okay, let's leave it at that for today. So if we return -1 here. Now let's check what happens if we run our code on this tree. So this is not equal to null. So we return the height, the maximum of the height of the left subtree. Left subtree has height -1. The right subtree has height -1. And then we add 1 to that and we return 0. So it does the right thing. In fact, sometimes these recursive algorithms, actually the base cases tell us something about our definitions of things like height and size and so on that we weren't quite aware of. Like that the height of an empty tree, it only makes sense to have it be -1. That's the only thing that makes sense. Okay. All right. So if we take a look at these algorithms. All right. So well, a couple of things. So one thing that I showed you is that a node is this thing that probably has a right pointer and a left pointer. And actually, in many, many cases, it makes sense to also have a parent pointer. So it just can be very handy to have this pointer back up to your parent. So one example is, what if I ask you to write a function that returns the depth of the node u in the tree rooted at R. So that's a picture that looks like this. Here is R, somewhere in here is u, and I'm asking you for the depth of this node u in that tree. So how would you do that? Yeah.
Just return 1 plus the parent, 1 plus the depth of u dot parent R.
Yeah, so you could use recursion and say, I will return 1 plus the depth of u dot parent back up to R. So that's u dot parent. So there's this length of this path plus 1 is the length of the path to u. What's the base case?
U equals R,
Return 0. Yeah. The root has depth 0. The depth is the distance to the root. If you are the root, you're at distance 0 from yourself. So there's a recursive algorithm. Is this maybe an overuse of recursion? Could we have done this really easily also without recursion? What are we doing here? What is this recursion doing? It's walking from you to you's parent, and then it's going to walk to the parent of that, to the parent of that, to the parent of that. So we could rewrite this with something as simple as a while loop. Say d is equal to 0 while u is not equal to r. Increment d, and u equals u dot parent. That does the same thing, right? So we start, the depth is 0, d is equal to 0, and then all we do is count how many steps we have to take up until we reach the root. Okay, so there's one thing that parent pointers are handy for. And, you know, for some reason I made a little fuss about this. Why, why not use recursion? Well, if you've worked in Python before, or actually any language, recursion is fine as long as you have some reason to believe that you won't be making a lot of recursive calls, so a deep set of recursive calls. And, you know, if all we're talking about is trees here, even binary trees, you know, the depth could be very high. The depth could be 1,000,000. In fact, you know that, of course, a list, you can also think of a list as a binary tree. Instead of successor, you just call that right, and that's a list, right? That's a binary tree. So binary trees can have high depth. And if you've worked in Python or in some other languages, this would lead to a recursion depth that's equal to the depth of the tree. In fact, all of these would. And what happens if the recursion depth gets too high? Yeah. Yeah. So there's a programming question and answer site whose name is exactly the thing that happens. Stack overflow. You blow the stack, and that's a really bad thing to do. You know, people have died because of stack overflows, and that's even recently one of the constant acceleration in the Toyotas for I don't know, maybe 5 years ago was traced back to a stack overflow in the code that controls one of the sensors in the accelerator pedal. So that's literally some people crashing into each other because of a stack overflow. So people dying. So we want to avoid stack overflows. And actually, that means that if we're working on trees that we don't know anything about, and maybe they're really deep trees with high depth, then we'd like to avoid these kinds of recursive functions. They're great because they're easy to program, easy to understand, but you know, you can kill people with them. So let's not do that. Let's think about another way of doing this kind of thing, like we did here. Right here we had a recursive function and we somehow managed to turn it into a while loop. No danger of a stack overflow in this code, but there is a danger here. Now, unfortunately, these other functions we wrote, they're not quite so simple. What's the difference between this function and, let's say, this one? Yeah.
There's only one path for the depth, while for size, we have to keep track of 2 different paths.
Yeah. So it's actually, this only makes one recursive call, and it's not quite as relevant, but that recursion is at the tail, so it's actually really easy to unwind. It's called tail recursion. These guys make 2 recursive calls. That is much trickier to get rid of. But let's see how we can do it by tracing the execution of one of these algorithms. So draw us a tree here. Let's leave it at that. And let's run this code for size. So it starts with r being equal to the root, and then it makes a recursive call on the left side. So it does this kind of thing. Well, that recursive call on the left side starts with this thing as the root, and it makes a recursive call on the left side. That thing makes a recursive call on the left side, which immediately returns the value 0. So a 0 comes out of here. Now we're back up to here. This makes the recursive call on the right side, which immediately returns the value 0. Now this thing returns 0 plus 0 plus 1, and that's what comes up here, the value 1. Now back up at this level in the recursion, this thing has already recursed on the left side. Now it's going to recurse on the right side. That's going to recurse on the left side. That's going to recurse on the left, which will come back right away. To the right, which will come back right away. Back up to here. This has already recursed on the left, so now it's going to recurse on the right. Return, return, return. And the picture looks like this. So if I follow this path here, put some arrows on it so you know which direction to follow it in. This is really what the recursion is doing. It's tracing this path. So what I would like to be able to do is to trace this path without using recursion. Okay? So if I look at a typical node in this picture, isolate it from the rest of the picture, it looks like this. It has a parent, left child, and a right child. When we first arrive at this node, where are we coming from? First time we see this node. So in this walk here, this purple walk around this tree, maybe this node that I've drawn here is actually this one. When is the first time we see it? Where did we come from? So we came from the parent. And if we come from the parent, where do we go next? We go to the left child. Okay? And then when do we see the node again? Walk around down here for a while, and then we come back from the left child. And where do we go next? We go to the right child. And then the walk disappears for a while. And the next time we see it, we come back from the right child. And then what happens? Then we go up to the parent. Okay? So if we're making one of these walks, and we arrive at a node, the only thing we need to know where we should walk next is which node we were at just before this. Okay? So let's see if we can turn that into some kind of working code. It won't actually be working code because there's these null nodes are a bit annoying, but we'll write something that looks like it works. And if you want to see actual working code, you can look in the book. So here's some code called traverse R, which takes this walk traverses the tree rooted at R. Okay? So we said that we need to know where we have come from. So we need something like a previous node. And let's start by setting the previous node equal to, I'll just say